Integration by parts is a method used for solving indefinite and definite integrals of the form the integral of f of x times g of x dx. So it's important to know that integration by parts doesn't allow us to solve all integrals of this form. So there is no product rule for integration, but it allows us to solve a certain type of integral that has a product as its integrand. So the formula for integration by parts can be derived from the product rule. The product rule for derivatives. So the product rule for derivatives is given right here in the center. So the derivative of f of x times g of x is f of x g prime of x plus g of x f prime of x. So to get the formal integration by parts formula, we're going to start by integrating both sides of the product rule formula. So that's what we see right here. We're taking the integral of both sides of the equation. And on the left side, I have the integral of the derivative of the product f of x g of x. And here we should be thinking the fundamental theorem of calculus. So an integral and a derivative are inverse operations, so they cancel each other out, and I end up on the left with just f of x times g of x. And now when I integrate the right side, which is the integral of a sum, I can split that up. So I can do the integral of f of x g prime of x plus the integral of g of x times f prime of x. And now we're just going to do some rearranging. So to get to the next line, what I went ahead and did is subtracted this red portion here. So the integral of g of x f prime of x, I subtracted it to the other side. So we have this blue portion, f of x g of x, minus the integral of g of x f prime of x dx is equal to this black portion here, so the integral of f of x g prime of x dx. So underneath each little part, you'll see labels. So we're calling f of x, the function f of x, we're going to call it u. And this whole portion here, the g prime of x and the differential dx, I'm calling that dv. So the left side becomes the integral of u dv equals u times v. So v itself is the function g of x, and then minus the integral of v du. So we call g of x v, and then f prime of x is du. So this is the formal integration by parts formula, but we're going to go ahead and take a look at it just by itself on the next portion. Alright, so here is the integration by parts formula right now just for indefinite integrals. So if I have the integral of u dv, that equals u times v minus the integral of v du. So it looks a little different right now than how our standard integrals would look, and that's because what we're really going to need to do is analyze an integral of the form f of x times g of x, so that's the integrand, and we're going to need to determine the parts for integration by parts. So we're going to need to find this u, so u is that f of x function, and we're going to need to find dv, which is the g of x dx portion. And so here are a couple strategies and tips for choosing the u and the dv. So the u should be a function that can be easily differentiated repeatedly. The derivative of u should be nicer than u, so we're looking for the derivative to be a more simple looking function than the original. The dv part should be a function that can be easily integrated repeatedly. And if the natural log of x is in the integrand, we're always going to let the u be the natural log of x, because we don't have an integral for the natural log of x, but we do know the derivative of the natural log of x, which is 1 over x. So these are just going to be a couple of strategies and tips for choosing the u and the dv in order to apply this formula. So this is a formula here that you're going to need to memorize. The integral of u dv equals u times v minus the integral of v du. Okay, and now let's look at some examples. So we have the integral of x times cosine x dx. Let's first talk about the fact that so far we don't have a strategy for solving this type of integral. So we can't use substitution because we don't have an inside function here. Now, if this was cosine of x squared, then we can go ahead and let u be x squared, and then the derivative is 2x, and we can modify that and apply the substitution method. But we don't have the right setup for that. I do have a product of two functions, though. I have x times cosine x. So I'm going to go ahead and apply integration by parts, which means I need a u and I need a dv. So the strategy for choosing u was to find a function that's easily differentiable. So my options here are to choose x or to choose cosine x. Well, both are easy to take the derivative of. The derivative of x is 1, the derivative of cosine is negative sine. But remember, the second part to the strategy was I want the derivative of u to be nicer or more simple than the original function u. So the derivative of x is 1, and so 1 is a little nicer, more simple than x. Whereas if I take the derivative of cosine x, the derivative is negative sine x, which is sort of along the same lines in complexity. The cosine function, negative sine function are both trig functions, but taking the derivative of x gets me just 1. So I'm going to let u be x so that dv is everything else. So cosine x dx. And then what we're going to need to do is we're going to need to find the derivative of u. So the derivative of u, as we just said, was 1, but since the variable is x, it's going to be dx. So du equals dx. And then I'm also going to need to find v. Well, v is the integral of this second part, my dv portion that I chose, my cosine x dx. So if I have dv, in order to get back to the original function, I would have to integrate. So what I can think about this as, this is a differential equation. So this, you don't have to write this down, but what we're thinking of is I can divide by the dx. So in other words, dv over dx equals cosine x. So if I wanted to solve this, this is a differential equation. So v is negative sine x and then plus c. So from right here, we don't need to show this work. What I just need to show is what the v function is. So v is negative sine x. And what we're going to do is we're going to go ahead and drop the plus c. So we're not going to apply it until the very end of the problem. So this is an indefinite integral. It will have a plus c, but we're not going to confuse ourselves right now and include it when we solve for v given the dv. So all of this right here, this is my scratch work. So I'm just going to put it in a little box in the corner. And so now I have all my information in order to apply the integration by parts formula. So I'm going to jump straight to this equals, so the formula was, so remember this is u and this is dv. So the formula was this equals u times v. So here's my u, which is x, and here's my v, which is negative sine x. So I'm going to write that as negative x sine x. So this portion right here, just to remind ourselves, this is u times v. And I just elected to write the negative in front. So negative x times sine x is u times v. And then the rest of the formula is minus the integral of v du. So I'm looking at these two portions right here. So v is negative sine x. And then du is dx. So now my original integral, so my u dv, the integral of u dv equals u times v minus the integral of, so this portion here is v du. So now it's a matter of simplifying this and really solving this indefinite integral that's remaining, but notice it's a nice indefinite integral. So we'll go ahead and rewrite this. So I have negative x sine x. So now these negatives become positive, so I can pull out the negative in this one. So this would be plus the integral of sine x dx. So now the integral of sine x dx, so I still have to bring down negative x sine x, and the integral of sine x is negative cosine x. And since this was an indefinite integral, we're going to include our plus c. So this is my answer. Alright, so now we have the integral of x times e to the x dx. So again, we cannot solve this integral with the substitution method, and we have a product. So we have x times e to the x, so we're going to try integration by parts. So we're going to need our u and our dv. So our u, we're going to again choose to be x, because the derivative of x, again, is 1, which is nicer than the derivative of e to the x, which is the same function, not a simpler or nicer function. So we're going to let u be x, and so du, we'll just jump straight to writing that, is dx. So the derivative is 1, so 1 dx. And then we're going to let dv be e to the x dx. And remember, for dv too, I want something that's easily integrable as well. So the integral of e to the x is just e to the x. So that allows me to find v easily as just e to the x. So now here is my scratch work, or my parts, all the parts that I need to apply the formula. So now this was u times v, or I need u times v, so we have x times e to the x minus the integral of v du. So v is e to the x and du is dx. So again, so this portion here is u, this is dv, this here is u times v minus the integral of v du. So now I just have to evaluate this integral, which again is nice. So my final answer here is going to be x e to the x, and then minus, well, this integral is just e to the x, and it's an indefinite integral, so I have to include the plus c. So if I wanted to here, I could go ahead and pull out an e to the x from what's in these left two terms. So I could write this as e to the x times x minus 1, and then plus the constant c. Alright, so now I have the integral of the natural log of x over x to the 9th dx. And so again, we can't solve this with the substitution method. If there were just an x on the bottom, we could let u be the natural log of x, so the derivative is 1 over x dx, but I have this x to the 9th in the denominator. So we're going to apply integration by parts, and if at first you're thinking, well, this is a quotient, not a product of two functions, we could in fact rewrite x to the 9th as x to the negative 9. So I could think about this as the natural log of x as one function, and then x to the negative 9 as my second function. So my options for u are ln x and x to the negative 9. But now remember, the fourth strategy was any time natural log of x is in the integrand, we have to let it be u. Because if I attempted to let it be dv, I don't have an antiderivative of the natural log of x. So I'm going to go ahead and write u as the natural log of x, and then jump straight to, well, then du is 1 over x dx. So dv is x to the negative 9th dx. So v is the integral of this function. So I'm going to have to add 1. So I'm going to get x to the negative 8, and then divide by the new power, so negative 8. So now here is my scratch work. And now I'm going to need to apply the formula. So remember, this portion here was our u, and then this whole portion was our dv. So the integral is u times v. So u is natural log of x, and v is x to the negative 8 over negative 8. So u times v, I'm going to write that as natural log of x on the top, and there's a negative 8 in the denominator, and I'm going to move the x to the negative 8 to the bottom and make it positive. So this portion here, this is my u times v. Then I need minus the integral of v du. So these two portions here multiply together. So v, I'm going to again rewrite as, I'm going to put a 1 on the top, or a negative 1 on the top, and then 8x to the 8th, and then times du, well, that's 1 over x dx. So here's my v, and then here's my du. Alright, so now I'm going to simplify this before I do the antiderivative. So this portion on the left stays the same. I have ln x and then over negative 8x to the 8th. And there's a minus here and a minus here, so I'm going to write this as plus the integral of 1 over 8x to the 9th. So here on the bottom, if I multiply these, I would add their exponents. So I have 1 over 8x to the 9th dx. So now, again, the x to the 9th can be rewritten as x to the negative 9. So this is plus the integral. I'm going to write this as 1 over 8 x to the negative 9 dx. And so if I integrate this, I'm going to get 1 over 8 and then x to the negative 8 divided by negative 8. And we still have to continue to bring this down every time. ln x, negative 8x to the 8th. And then ln x, negative 8x to the 8th. And so now we can just combine this, and we of course need our plus c. So our final answer is going to be natural log of x over negative 8x to the 8th, and then minus, let's see, the bottom is going to become a 64. So I'm going to write this as 1 over 64x to the 8th plus c. And really, we don't need to simplify from here. This would actually be a multiple choice question, and the answers are written similar to this. So we don't need to worry about combining and creating common denominators between the first two fractions. So again, integration by parts, just to recap, we want to always try to see if we can use the substitution method first. And when we can't, if we can try to recognize it as a product, and we can see a function that's easily differentiable and easily integrable with the other one, then we want to try to apply the integration by parts method. Alright, so now we're going to look at integration by parts with definite integrals. And you'll notice it's the same exact formula, but now with limits of integration. So the integral from a to b of u dv equals u times v from a to b minus the integral from a to b of v du. So now we're going to go ahead and take a look at this example. So I have the integral from 0 to 2 of x times e to the 9x dx. So let's go ahead and choose our u to be x and our dv to be e to the 9x. So now du is dx, and v, so the integral of e to the 9x is 1 over 9 e to the 9x. So here's my scratch work. Starts out the exact same way as indefinite integrals. And so now when we go ahead and apply the formula, we're going to just make sure to include the limits of integration from 0 to 2. So we're going to have u times v, so x times 1 over 9 e to the 9x. So I'm going to write that as 1/9 x e to the 9x. This is going to have to be evaluated from 0 to 2. Minus the integral from 0 to 2 of v du. So v du is 1/9 e to the 9x dx. And so now I would need to evaluate this integral and apply the limits of integration. So here the antiderivative is going to be, so again, 1 over 9. So I'm going to end up with 1 over 81 e to the 9x evaluated from 0 to 2. And then this portion would still carry down as 1 over 9x e to the 9x from 0 to 2. So now it's just a matter of simplifying at this point. So remember, we plug in the top limit of integration first. So I would get 2/9 e to the 18 minus, so if I plug in 0, well, that whole term would be 0 because of this x right here. So now we really just have minus 0. So I'll just put a parentheses around that. That was evaluating the first part's limits of integrations with the limits of integration. And now we're going to do minus, plugging in the 2. So we'll get 1 over 81. So I'm going to leave this minus here on the outside. So 1 over 81 e to the 18. and then minus if I substitute in 0. So now I won't get 0 because if I plug in a 0 to the e function, anything to the 0 is 1, so I will get 1 over 81. Whoa, I don't know why I did that. 81, and then close parentheses. So now here, let's see, can I do any simplifying? Yes, so 2 over 9 would be, if I make common denominators, this is going to be 18 over 81 e to the 18th. So I'm trying to force 2 over 9 to have a denominator of 81 because now I have minus 1 over 81 e to the 18th and then plus 1 over 81. So this negative has to distribute over here to this negative. And so now I can combine these together. These are like terms. So 18 over 81 minus 1 over 81 is 17 over 81 e to the 18th minus 1 over 81. And now that is my final answer. So adding in the definite integral just means that our final answer is of course going to be a numerical value, and it may add a little bit of simplifying to the job, but it's still the exact same integration by parts formula. We just have to remember to plug in the limits of integration. The last thing that I'll leave you with is, we didn't go over any examples of, well, what happens if you choose incorrectly? So if you accidentally choose the other function for u, and then the remaining function for dv, it's just not going to work out. You'll realize that when you try to integrate the v du portion, that you're going to have left yourself with something that you don't know the integral of. And so that means you're just going to need to go back and switch. So keep that in mind. But again, if you try to follow the strategy, that applies to most of the integrals will apply integration by parts to. But if it just so happens you end up with something difficult to integrate over here in this v du portion, then you probably chose the wrong u and dv, and you just need to go back and switch them.